There you go.
All right, so thanks everyone for joining us again for the third session of MCS 2111 MCS seminar. So we'll have the, again, just to reiterate, sort of the expectations is for those who are in the class, is to attend the lectures. Of the planned 8 seminars that we will have, you'll be responsible for writing up reports on 2 of them. Just need those by the end of the semester. If you want to start writing them earlier, obviously that could maybe mitigate some of your workload later on, but end of the semester is fine. So 2 of the 8, you will write just a page, maybe cap it at 2 pages. So somewhere a page or 2, just sort of outlining what the talk was on, what you liked about it, and what, if you were to do a senior project on that, what you could imagine doing with that research area that will be described by the speakers. So without any further ado, and I guess I should say you can give me, of course, or me or Paula, Professor Lauren, an email if you want any more clarification on the expectations or have any further questions. But without further ado, I'll introduce the speaker for this session, who is Paula Lauren, who will be talking about extracting meaning from text using word embeddings. So Professor Lauren is an assistant professor in the Department of Mathematics and Computer Science here in her 4th year at Lawrence Tech. Her research is in the area of text mining, which is an interdisciplinary field that crosses many disciplines such as machine learning and natural language processing, just to name a few. Paula received her PhD in 2018 from Oakland University in Computer Science and Informatics, where her thesis was on the optimization of word embeddings in text categorization. Paula received her master's in computer science from University of Michigan Dearborn and bachelor's degree from Wayne State University. She also spent 10 years in industry, starting as a programmer and leaving as a software engineering manager before embarking full-time on her PhD. Worth noting, Paula has also designed and developed a course in text mining at Lawrence Tech, and this fall will be the 5th time she will be teaching it. So if anybody from today's talk is interested, MCS 4993 or MCS 5993 special topics in text mining and analytics would be a great course to take. So with that said, Paula, I hand the floor over to you.
Thank you so much, Matt. Appreciate the introduction. Okay, so the plan is so the overview for today's talk, we're going to kind of divide this by 2 parts. We'll spend the most time on part 1 with research, get into understanding a little bit about what text mining is. That's a good place to start, and then delve right into the seminar talk for getting meaning from text using word embeddings. Probably we'll need to get into what are defining or unpacking that, what are word embeddings, and then talk about some libraries and methods that can be used, and then the applications, and there's many applications for word embeddings. And then I'll have a Q&A at the end of the seminar talk, so you can ask questions specific to the talk itself. And then I'll get into the research projects, and then of course have questions at the end of that. And then the last part the second part with teaching, this would be, less time on this, as mentioned, more time on the research, talk about the text mining and analytics course. As Matt mentioned, that was something that really ties into this area that I'm going to talk about. And then kind of my methodology for senior projects and directed studies, and also have a Q&A on that. And actually you can ask questions at any time pertaining to, each part, whatever is of interest to you. All right, so let's get started on text mining. Now, this is truly an interdisciplinary study. So I really like this Venn diagram. It really crosses over and just shows the interdisciplinary of text mining. So kind of just looking at, starting from data mining. So data mining is a discipline. So these are the main outer ones are definitely disciplines in their own right. And data mining is all about discovering patterns. So the idea is discovering them in large data sets. And we're going to be using methods that intersect with machine learning, statistics, and database systems. Now, document classification, that evolves automatically. So we're going to automatically assign a label to a document. That would be referred to as that. And then document clustering is when we don't have the label. So we're going to try to figure out what that label should be. Another categorization for this would be unsupervised learning, this would be unsupervised learning. Classification is actually supervised learning. Let me take that back. Classification is supervised learning because we have the label to train on. document clustering. So clustering would be unsupervised because we don't have the label, and the objective is just trying to find what that should be. All right, so moving over to AI and machine learning. Now, which is artificial intelligence, that is really kind of more of a superset. Like that would be the overall umbrella term that machine learning is a subset of. Now, AI, kind of the general categories and pertain to recognition tasks and reasoning tasks. Now, machine learning as a subset deals more with recognition tasks. And what does that mean? It's about automatically learning from data. All right, we're automatically trying to figure out what those patterns are without explicitly programming. Okay, so that's the key thing. And then reasoning tasks would be a type of like expert systems. This is where the rules would be explicitly stated. Okay, and now information extraction, that we see this kind of interfacing between the text mining and the machine learning. That really is about automatically. We want to automatically be able to identify entities or topics between text. So moving on to computational linguistics, this is the scientific study of language from a computational perspective. And then this intersection here with natural language processing, that is the study of the interactions between computer and natural language. And then looking here, this concept extraction, that's about grouping words and phrases into semantically similar groups. So we can kind of see how they're intersecting here. Now, library in information sciences, that deals with organization, accessing, collection of information, and information retrieval. So that we see the intersection kind of and they all pretty much intersect with each other. That's involving methods dealing specifically with accessing information. And we can think of, we use it a lot in text mining pertaining to search. Okay. Oh, I see I have a question that came up. Are
Yes.
you allowing questions? Yeah, you know what? That's fine. You can ask questions. Yes, you can ask questions during the talk as well. Okay, that's perfectly fine.
Okay, thank you.
Yeah.
What is the difference between information extraction and concept extraction? To me, it seems they intuitively are the same thing.
In a sense, yes, that's one of the things with how they present this is I kind of would see there's a little bit of the overlap, and I actually even went to look at the precise definition of how computational linguistics, and they see it as more of this grouping of words and phrases into semantically similar groups. That's kind of how they distinguish it. All right, and then information extraction is specific to identifying entities or topics from text. So yeah, so there's just this minor distinction. Now, if I were to redo this, so this was the best representation I could find. Yeah, I probably would group in. I would take the concept extraction, kind of roll it, because there's definitely overlap. That's interesting. You picked up on that right away, because yes, I could see there could be terms that could fall under both. One thing I want to also add, since you pointed that out, what is missing from this Venn diagram is showing the mathematics and what plays a significant role across each of these. Data mining is heavily statistics, a lot in computational linguistics. Yes, it does have the statistics, but there's a lot more probability that's based in there. Okay, so there's, and it's interesting that you bring that up. Was that David?
Yes.
Okay, that's interesting you say that, because how do we there's a lot of times machine learning is used synonymously for data mining, and then we hear data science that is really, it kind of overlaps. Okay, so is it data mining? It's kind of machine learning. So there's a lot of this overlap that just goes on. And then, I just wanted to pick a representation that kind of really, just at least covered the key, gives kind of that interdisciplinary. But yeah, you bring up a good point. There is such an overlap, they both kind of fall. And it kind of even shows, you can see it's kind of overlapping with this. And then natural language processing, that is pertaining to interaction, the study of the interaction between the computers and human language. So that kind of goes with that. All right, so going on to library, so I already touched upon that. And then databases here, that is a collection of structured information. So this would be our data. We want data to be easily accessed, managed, modified, updated, controlled, and organized. Okay, so that's why the overlap and with, as we can see, they all kind of intersect there. Okay, and then let's go to this one that kind of crosses the web mining. All right, and so web mining, that would be the application of data mining, right? So it's data mining techniques that are being applied to discover patterns. And this is, and we kind of can get an idea of what is that web part of it. So it's data mining, right? And it's applied to web. So this is web text that's available on the web. And we can say definitely within the past 10 years, there's been an overwhelming, right? It's social media has been driving a lot of that. All right, so I do see a question. You could just put a box around, you could just put a big box around everything and label it math. You know, who said that? Chris, that would be, math is a universal set. Yes, that would be, yeah, really, exactly. That's a good point. So why don't we do this? Why don't we update this? This would be a good update to this, right? So this was, because this was the best one. I was trying to find something that really kind of, covered, and I thought it was more representative than not. But yes, to bring in the math, we can really, there's a lot of math that we can bring in, right? The probability statistics, overall math, linear algebra, and we're going to get into that. So there's a lot of, so thank you. Yes, thank you for that comment. Okay, all right. So oh, I didn't finish. So now I got to talk about text mining. So now we kind of covered everything. So we see text mining sits in the middle, right? And it's automatically processing. So that's about the automatic process and extracting valuable insight from the text. It's all about the text. So we're applying methods. We're crossing, pretty much crossing the board. All right. And in order to do that, because text is unstructured by definition, right? We don't have any type of structure to it. Data mining, a lot of these other methods, they have to have some type of structure. So data mining also is about transforming this natural language into a form that computers will be able to understand and word embeddings are one way to do that. All right, so probably most people have not, word embeddings have heard of it. Word embeddings are probably really starting to it appeared, right, in the literature, really started in 2010. And actually it appeared in an early paper, was with Bengio. He actually won the ACM Turing Award a few years ago. And he introduced it but it really didn't start taking off. You can kind of see this ascension here. Now this is a really cool application. It's a Google Books Ngram viewer, and it tracks Ngrams over in books, right? It looks at all of them and how much they appear. Now, what is an Ngram? So that is that belongs in computational statistics, or excuse me, that's a term from computational linguistics. And what it is a contiguous sequence of N words from text or speech. All right, so this gives us an introduction to something called a language model. All right, so what a language model is, it's about predicting the next word given the previous word or words. All right, and so when we talk about an Ngram, we'll usually say we're talking about N is it equal to 1. So if it is equal to 1, that would be a unigram. If it's 2, bigram, 3, trigram. So word embeddings, that would be a bigram. Okay, so they went through text, and it's just interesting to point out. So I went full-time for the PhD right about here. And that's when, and it really was only known. Word embeddings was something that existed in, pure academia. Really, it has started to make, its way into commercial applications. But so that's the word. And this only goes to 2019. So I'd be interested, once they update it for at least 2020, 21, I would imagine, it's just going to continue that ascension because of the importance. There are other terms as well that I remember from the literature at the time: entity embeddings, sentence embeddings, document embeddings. That's what you're seeing here. It kind of looks like it's flatlining. So what you're seeing here, I just redid it just remove the word embedding so you can see like sentence embeddings has a little more appearance in the literature over the entity embeddings, but not by much. All right, just something to point out there. Oops. Okay, so what are word embeddings? All right, so we see, so it's a relatively new term, right, in the literature, and we have this, so summing it up, this numerical representation of words. Yeah, and this term distributional word vectors. Also, I see distributed word vectors, and so there's low dimensional representation of words. So there's a lot of really a lot of terms there. But the key idea, it's word pair co-occurrences. That's what it really, all right, it really is about. That's what it's capturing. Word pair co-occurrences that are extracted from a corpus, a body of text. All right, that's what we think of a corpus. Now, Google News makes available pre-trained worded vectors. So and we'll talk about this in the next slide, created by Word2Vec. And they have pre-trained, it's like 400,000 word vectors that I just downloaded. And out of all the words and entities available, there's a reason why I chose mosquito. Just curious, does anyone remember my question for Dr. Pell's talk? I guess we can do a hand raise. Anybody remember? Dr. Pell remembers.
Sorry.
Remembers. That's okay.
Sorry.
That's okay. No problem. The question that I had, so during his talk, so he does research, right, in trait modeling viruses, right, and how they. Oh, someone has a question. Let's see here. Something about. It's about the meaning of a word. It's a. Okay, something about. Okay, so let's get. Trying to read. Okay, so yeah, so the question, so Dr. Pell's talking about transmission of diseases, and he mentioned this mosquito vector. And if you remember, so my question was, so my imagination is just like vector, mosquito vector, what's being tracked in this mosquito vector? What, vector, we think of it as a mathematical, right, term. It's a mathematical quantity, typically, in terms of the true, essence of it, it captures, right, magnitude and direction, right, the essential vector. And I thought, so I was like, what is it? So in my mind, I'm thinking, okay, is it capturing the speed of the mosquito and then the direction it's going? And then how is it doing that? So that was my question. What exactly is contained in the mosquito vector? And that's where it's from the biological domain. So these are called biological vectors. And in that context, the term context, we're going to see that repeatedly. We're going to hear that concept come up again, all right? In that context, it means, biological, a vessel for communicating disease, right? And also vector-borne diseases, right? So these are vectors as a vessel to communicate it. Okay, so that's the reason why I chose mosquito. And so what I did is so I downloaded these vectors, word vectors, and so this is what it looks like, a word vector, an example. So you see it's a numerical representation, and we don't see all of them here, but these have 300. All right, this would be called a 300-dimensional word vector. That's what we would refer to that as. Okay, so let's get into creating word embeddings. There's two popular methods, all right? The two main ones that really, during the PhD that just really hit, the research one came out of Stanford, that's global vectors, and then Google, now it's a Word2Vec, okay? And one is considered a count-based method, and then one is a prediction-based. And count-based is because, well, it's really more, they construct the matrix first and then apply dimensionality. And then the prediction-based is using a neural network. Oh, one thing I forgot to do is add the reference. This is taken from the paper. I have the links to it. So these are the links to, and the slides will be made available for the talk, so you can click on that. But for the prediction-based method, these are the two flavors, if you will. One's called continuous bag of words, and what that's about, think about, right, the idea of this language model, predicting the next word given previous words. It's given the sequence, all right? So this would be a sequence of words, and there's a summation going on of the vectors, and then we're going to try to predict. It's going to try to predict what that target word should be. And then skipgram, it's kind of reverse. It's starting with the word, initial word. It's going to try to predict the context. That's kind of the key idea. All right, just keeping it very simple. All right, there are 3 key parameters. There's a few others, but the 3 ones we want to focus on. The 3 key user input is something called context window size. And what that has to do, we can think about it. Again, what is the word embedding? This is about word pair co-occurrences. And that window size is important because it's going to determine how far to the left, to the right of the target word that we're looking at should we be looking at. And we're going to try to keep those counts, those frequencies of how many times that exists in a corpus. All right. And the word vector size is a parameter. It's going to tell us the size of the dimension. What is the dimension we're looking at? As I mentioned here, the pre-trained word vectors, they have, that was 300. So this was made available. They trained it on 300 to give us 300 dimensional word embeddings. All right, so that's the word vector size. And then another input, this is a very important one, key user input parameters you have to set, is called the minimum word count. And what this does, it decides how many words, how many times the word should exist in a corpus to have inclusion in the vocabulary. All right, and that vocabulary is important because that's going to determine the rows and the columns of the matrix, as we will see in a moment. Actually, let's get right to that. So let's create word embeddings, just go, and this is just to be for illustrative purposes, showing a simple example here. All right, so we're going to looking at it from the count based. This is constructing the word context matrix. And we would typically have some pre-processing because when we're dealing with any text, right? Because we're working with text, we have to do some kind of pre-processing. What does that mean? All right, so I kind of show you here an example. We have an original sentence, and then we have the pre-processed sentence. And what this is doing, it's some pre-processing that's being applied here is tokenization. That's where you're seeing is kind of breaking it down to individual tokens. And then we see what else is being applied? Punctuation removal, right? We've removed the period here. And that, and lowercase conversion, right? So Michigan is lowercase. And pre-processing methods is completely, there's no rule where you'll see some, don't apply some things, right? One thing I could have done, I didn't do is lemmatization or stemming, where it's reducing this word viewing to its essential, right? Its core word, which would be view. All right, so I didn't do that here. And again, just to keep it simple. All right, so that would be a pre-processed. Let's look at this min word count. Let's say hypothetically I make it 5. That means the number of times so we're just given this hypothetical corpus with a lot of things on artwork, lake, Michigan, and sun. So kind of the general concept of that corpus. And let's say the word exists. We're looking for how many times the word exists in the corpus. And let's give it a minimum word count of 5. All right. And let's just say these are the words that exist: artwork, lake, Michigan, sun. That meet that threshold. So those become the columns and the rows of our word context matrix. Okay, now let's understand the word or the window context size and what that's all about. And I mentioned, right, it has to do with this is what makes this an important what we have to define why it's important, because this is determining how far to the right and left of the word to look, all right, to determine what the count should, to determine if that word pair co-occurrence exists. So let's look at this. Let's look at our pre-processed sentence. Oh, and another thing, I didn't remove any stop words here. All right, stop words would be words that don't contain much, information, right? By, the, there's not much information content in. Actually, I would have removed it. All right, I would have removed it because that would have existed in the matrix. So yeah, so hypothetically, I would have removed it, but let's just keep it simple again and looking at the word context size of 3. So what I'm going to be doing is looking at a word. So it's going to process every single word when it's building the word context matrix and count. So how many times? So it's going to look at a maximum context size of 3. So that's 3 words to the left and 3 words to the right. So if we look at artwork, we see, so count 3, 1, 2, 3, lake exists within its context window size. So we're going to want to count that. So in our matrix, right, so we have our artwork and lake, we're going to add a count there. So there's something there. So we'll just keep it simple. We'll just say 1 for now. All right. Or just keep it simple altogether. And then we look at lake, right? So lake, we can see, and similarly, so lake in artwork, and it's going to add a word or a co-occurrence pair, a frequency count for that. Similarly for Michigan, right? It's all within its window. All right. But sun, right? Because keep in mind, we're looking at a window size of 3 words is surrounding. Artwork is not going to be in there. It's not going to be surrounding unless it is within that 3 word distance. Okay. All right. So that is covering that. And then the other important parameter, or, I should not use the word parameter because that has a different meaning in neural networks. It has to do with the weights in the neural network. And I should be using the term hyperparameter. That is, probably should stick with that one. So anyway, so the word vector size, let's say we want to make it 2, right? And again, very simple example to illustrate. We have a 4x4 matrix. So if we wanted to make it 2, we're going to reduce the dimensions, all right? And that's called dimensionality reduction, all right? And a very common approach for that is using something called singular value decomposition. And I see I have a question, David?
Yeah, sorry.
Yeah.
One of the things that stood out to me is that it seems like the X matrix will be symmetric.
Yes.
Yeah. So then that begs the question, why would we use singular value decomposition? Sorry.
Well, because we can still use it. It can be used on a symmetric matrix as well. Okay, so we can use it, and we actually use specifically, it's truncated. So in the research that I did, I used truncated SVD because why we want to reduce the dimension? No, we can use it. It can be used on a symmetric. Okay, so just so you know,
yes.
But why we do it? Why we reduce the dimension? Like the whole point of why we do it. Right, we can't appreciate with this simple example because it's just a 4x4. But we can appreciate when we're dealing with a matrix that's, let's say, they typically are going to be tens of thousands, hundreds of thousands. The Google the matrix that I drew the mosquito vector from, that's 400,000. So that had to have been at some point, we were looking at a 400,000. If we were gonna, look at it from a count basis, a 400 by 400,000. The problem with that is that it would be too computationally intensive to be working with these large size vectors. So we want to reduce the dimensions, and that will give us something a lot more manageable, computationally manageable to work with. Okay. So yeah, so that's the idea behind that. Okay, so now we reduce the dimensions, and so just a little this is just to unpack this a little bit. So U and V is going to give us something called orthonormal matrices. This has to do with orthogonal. Just a little recap for some of us who have linear algebra. Orthogonal, right? We can take the dot product, right? It's going to give us, we can take the dot product, that's going to give us 0, and then it's unit length, right? That's our orthonormal. The sigma has to do with our singular values. And this is a nice motivation for what you can see, the beautiful thing with linear algebra, what it allows us to do, right? There's a reason to learn those eigenvectors and eigenvalues. It has a lot of power. All right, so now we can extract. So now we have reduced dimensions, right? And now we have word vectors. Now we have vectors. Let's just be, very, very clear on that. And what do we know about vectors, right? They have some really nice properties. Okay, what can we do with vectors, right? We can add them. Oh, I don't know if this is coming across as boldface. It's not. This should be. Oh, it is good. Thank you, because we know, right? Vectors in the from the physics domain, it has the arrow. We typically see the arrow, but in the mathematics, right? We in math books we'll typically see it boldface, right? Thank you, thanks, because I was like looking at maybe it's my monitor or something. But all right, so yes, we have really nice properties. We can add vectors, we can subtract vectors, we can multiply or take the dot product, right, or inner product, right, of vectors. A really nice property, we can visualize them, right? We can plot them, and that turns out to be, quite useful. All right, and continuing on, some other nice things with vectors, we can apply something called the cosine similarity, and that turns out to be quite a nice nice metric. So what is this, right? Similarity kind of breaks down to, so if we're going to say U, and so we have our U and V vectors. Oh, I definitely see that's boldface there. We are taking the dot product, right? So this is computing the cosine similarity, dot product numerator, and then we're taking the norm, right, of each of these vectors, multiplying, and this is going to give us a scalar, all right? So we're going to get one number here. And all right, so this is just further unpacking it, right? Summation, summing square, taking the square root, you know, just a reminder what the norm and dot product is in a little more expanded form. Okay, going back to our nice mosquito vector, right? And then we got introduced to. So using this, right, the cosine similarity, we can find similarity of words. And looking at the mosquito, and this is using the Google, right, the pre-trained Google word vectors. These were the words that came back, right? These were the most similar. So again, it's going to be computing a cosine similarity on all of the word vectors. Okay, so we have 400,000 word vectors. It is, and this is using word2vec, right? So I use word2vec to do this similarity. So that would be a method. Oh, I should step back. This is using the GenSum library, which is a very nice library for doing this work. What we see here, right, for looking at these similar words, right, pre-processing was not done to do any lemmatization or stemming, right, because we could probably reduce these to all mosquito, right, so it kept them all in there, which is fine. That's what they chose to do. Another thing, we have bigrams captured, right? They looked at, they extracted mosquito population as a bigram, right, all similar. And then larvae, and I thought I saw trigram, West Nile virus. So I think the most is a trigram. I didn't see any quadgram. I think they call them quadgram. I've never really seen too much in quadgrams. I think the most typically is trigram. And another pre-processing done, so you can see they did not do any lowercase conversion. You know, again, that was their choice. But yeah, so that is using, right, again, seeing the nice properties of vectors. What we can do, you know, we're looking at it from specifically with words. And again, this is looking specifically at the vectors and returning that. All right, going to visualizing, right? Because we know we get some nice properties with vectors we can visualize. And so this is taking, so here was 10. So by default, GenSum's going to give you the top 10. You could go in there and add another argument, I believe, to extend it. Here is where it's rendering 20. So I have 20. So you can see all kind of this is just a really nice thing. So what is it doing? How did we go from 300 dimensions, right? Now we had to reduce it to 2 because we're seeing it, right? Visually seeing this here. And an XY, right? So X is the looking at the first feature. So what happened here? And then the second feature. What this tool does, so this is an application, that should be lowercase t distributed. That stands for T distributed stochastic neighbor embedding. This is an application. And I have the GitHub a link to that. What this is allowing, what these researchers did, they took the word vectors and they applied additional dimensionality and reduces it to 2 dimensions so you can visualize this. All right, so, but this doesn't really, what looks really cool if you see compare it with another word and just see the clustering take hold. I jumped ahead. Let's look at it with 2 words. So what I was thinking, I said, I'm going to compare something that sounds like mosquito, but totally unrelated, right? Moscato and mosquito, right? So these are, again, the word vectors from the Google word vectors. And you can see this clustering, right? So this is what we just saw on the previous slide. Clustering of the mosquito vectors, no surprise there. And then we can see the clustering of the wine Moscato vectors, and kind of interesting. I have to say, just working with word embeddings, it's a kind of a word embeddings is kind of a knowledge discovery, because sometimes I learn words I've never even, or concepts or things that I've not heard of, right? So looking at this, there's some wines that I've heard of: Cabernet, Dry Rosé, Merlot, right? Pinot Grigio, but there's wines I've never heard of. Has anyone ever heard of a Trebbiano? Trebbiano, Dolcetto. So Dolcetto, that one I knew has to be a sweet. So Moscato's a sweet wine. It has to be sweet, because I know Dolce. I know that Dolce means sweet in Italian, and I actually looked this up. And Dolcetto is also a word, and it means sweet little one or little sweet one in Italian. I thought that was cute. So again, so the point here, it is separated. So you see this clustering of words. So let's go back. Let's go back to our mosquito, our vector-borne disease vectors. Okay, word vectors. I see Bruce smiling there. Okay, so we're going to bring that back, and we see. So we see mosquito. Right, we still have our mosquito right here, right? We have our, I'm sorry, that's not our mosquito. This is our mosquito. So purple was our mosquito. Then I added rat. And we can see, right? Okay, I can see rodents, rats, mice, so those kind of class. Then we see this insect, not quite, so that probably should have, it's not perfect. This is an open research area. There's a lot of open research questions, so it did not. But the reason why it did that, okay, so why did it kind of move over into that cluster? Because it was trained on the training data, and that's where it saw, it was kind of a combination of word pairs that kind of leaned it over into this cluster. So it's kind of like, okay, it little bit headed over there. Okay, so so we can see that, and what I want to kind of bring attention to is this one, right? That's the emoji with the question, but we can't really see that. But let's go to the next slide, because I kind of call this. Does anyone see a problem here? Here's a moment.
A problem?
Yeah, well, what is so I went ahead into the word vector similar to mosquito, rat, and bat. I wanted to see the word vectors that pertain to our biological, right, disease-borne vectors. Okay, so these are similar words. They pretty much seem overall similar, but this one is not. And why is that? What are anything, do these look like bats in terms of mammals?
I see.
Okay. So we see the problem, right? And I actually had to look this up myself. I had to look, because I know, we know bats. It's not just, bat. There's a different definition. So it's actually Hawaiian hori is the only one that appears to be relevant to the bat that I was trying to view. And again, the reason why is because the data was trained on, though it had a lot more examples, right, that seemed to pertain to, well, I don't know, someone tell me, what is right-handed hitter, left-handed batter? What is there a sport that kind of, probably baseball, right? Yeah. All right, so there you go. So yeah, so there's a problem here, right? And so one of the early tools was something called WordNet. And what they did is they determined all these different, they extracted all these, different terms for grouping lexical entries, right, which are words. And what WordNet is a lexical database. And so this is what this researcher did. So it took WordNet, which is, again, so it's going to just give you all these definitions of different types of words, and it gave a visualization to it. And I was just looking at how they developed this, and you got to see it for yourself, because actually this is interactive here. You can move it around, but I just took a screenshot here of just specifically this, and then you can see the bat. You see all the different, right, what are the different groupings? Well, what do we can think of? Bat can be a cricket bat, a club, right? And then we can to clobber someone, right? A flutter, right? Bat one's eyelashes. So these are all different kind of associations for what are possible definitions, or words, or synsets is the term they use for the word bat. Now, the one we're interested in precisely is this one. I actually had to look it up because, again, I think you guys saw last week, I really don't have much of a background in the biological domain and zoology, virology, all that. But this is what we're looking for. This is nocturnal mouse-like mammal. Chiropteran is the word. And I actually Googled it. I just put the screenshot on top. It's a mammal of the order Chiroptera. If I said that incorrect, please correct me. So yeah, so that's what we're looking at. So it didn't pick it up, right? And so this is another application of word embeddings. It's something called transformers, all right? And so what they did is they incorporated something called positional embeddings. And this is actually a research I'm just getting into and getting an understanding of, but apparently looking at that should be a word there. It's disambiguating the words via location of the word in the text, okay? And then it's based on this transformer architecture And this will be something a little to invite you to take my text mining. We will be unpacking this in the text mining class, but just a little heads up, the transformer architecture, it is definitely a neural network architecture that gets deeper into something called attention models, bidirectional, and we'll learn all this, but big driver behind something called word embeddings. Okay, and what that is taking positional, segment, and token embeddings for this disambiguation task. And something that I'm really interested in is GPT-3, generative pre-processing training, I think is what that stands for. And that, has anyone heard, just raise a hand, anyone heard of GPT-3? Just curious. All right, so we have one. Oh, I'm not seeing everybody. Okay, so I just take it. Okay, at least I see a few people. Okay, so yeah, that is Elon Musk. He created that, and it just sold it to Microsoft, and they made available, publicly available GPT-2, which I just started work with it. But the key takeaway is that word embeddings were the precursor to this, all right, to making this possible. All right, so let's get into more applications, word embeddings, okay? And this has to do with emojis, and really cool because so this was an interesting book by the linguist Van Evans, and he talks about, emojis, from a linguistic perspective, right? It's an augmentation of natural language, right? And it used to enhance communication. And even though it has this, right, this icon representation, it does contain a textual description, right? And he talked about in the book, just this was actually back in 2017 of how pervasive emojis are being used in text. And at that time it was 7 billion that were sent. And I actually had to look it up because I knew that has definitely have grown, and today it's 10 billion that emojis that are being used, and just showing the pervasiveness, right, of emojis. In 2015, it was considered the Oxford Word of the Year. So they consider it a word, right? And again, because it has a textual description. And we know this emoji, right? It's the laughing face with tears of joy, right? So there's your textual. Okay, so looking at emoji embeddings, we can do the same thing, right? We can plot them as well. So this is an example showing, right? We can represent them as a vector, and we can still take the cosine similarity and find similar vectors, which is kind of cool. So this is just, again, just for illustrating, that's a heart with sparkles. And so this is a heart. They should probably expect them in an embedding space to appear closer together. Now, this is probably the coolest research, whoops, let me go to the next slide, that I've seen with emoji embeddings, okay? So same idea, everything that we just saw, leading up to with the words, the cosine similarity vector, all the properties that come with it, allows this. So what these researchers did, this is a recent, did word emoji embeddings. It was based on a large scale data set. And we could just look at this, right? We could see, yeah, it's not perfect, right? Because it depends on what it was, the training data. We know it comes down to word pair co-occurrences. And we can see definitely clustering. I don't know if this is coming across, but this are flat. Oh, good. Thank you. Flags. So these are, for the most part, these are international flag emojis, right? And so we could see some clustering here. Those are clocks, right? When we could see clustering over here. So there had been something that pulled it over in that direction, depending on the corpus that it was trained on. So people clustering here. What I thought was cool, kind of all your default emojis seem to cluster over here. Signs, hand signs clustering over there. So really cool. I thought that was a really cool application using emoji embeddings. All right, let's talk about another, I think this will be the last application, is recommendation systems. All right, really originated with Amazon, seemed to be the first to, with the book recommendation systems. We've all probably are very familiar with them. They're being used for books, movies, songs, right? Spotify, definitely. I see that a lot with, if you like this, you like that. And so that is a type of recommendation systems. So what I did is just looked at if I can build one, using word embeddings and see how that would work out. And so this is using the movie lens. So I use the movie lens data And I really like their mission. That was I thought that was a cool mission, and aligns with the theory and practice, right? And Lawrence Tech is all about theory and practice. And I really like that idea of an understanding using real people. So what we have here, just show you an example of a movie recommendation. So here's how that's the data that's collected. The Godfather, this is the movie, and this is the rating that was given. Okay, so this user gave it, so on average, I don't know how many users here, but on average, average of 72,000 ratings at 4.33 stars. And it definitely is a interesting movie. So, do we have a question? Oh, okay. So taking that, so what I wanted to, building this movie recommendation system using Word2Vec. All right. So this is the data. So they make their data available. Really cool. They make it fully available. And this was taken just a snippet of the data. So what you're seeing, so what in that snippet, so it's 100,000 records that there's more. I just kept it, very simple, 100,000 records. And so each user ID. So you see each user and what their rating is. All right. And so this is the code, just showing you specifically the code for how we train this. All right. So we have the Word2Vec, again, through using the GINSUM vector. I put the window size as 5. So what is that? So we saw previously, it's the surrounding words. We're trying to get those word paired co-occurrences. Vector size of 300. The min count, right? We know that pertains to the number of times a word has to exist in the corpus to have inclusion in the vocabulary. And then this is just specifying. So we say 1, that's for skip gram, we saw that. And then the other one would be the continuous bag of words. And then epochs, because this is a prediction-based type of model. Epochs, it's something integral to neural networks. It has to do how many times through the training data. It's like the training cycle that it's using to train the model. So this is building, and then this is it, right? It's just building the data or building the model for our word embeddings. All right, so I wanted to see what would be the top movie recommendations for The Godfather. And again, so this is it. And I thought that was pretty cool. The first one it gave back, and I didn't use too much data. I mean, it was just using the 100,000 records, and it's actually 600 users. All right, 600 users across that. And if you're familiar with The Godfather, it's a mafia type movie. Goodfellas is a mafia type movie, so that was interesting. That it came right off the bat. The first recommendation. The other ones, not sure. Well, I guess maybe Killer. That is, so that's a that movie. I kind of just did a quick look of it. It definitely has a hitman thing. So okay, so maybe it would probably have similarity. The Big Blue, not so much. I actually looked it up. It seemed to be more about the cinematography of the ocean, the great ocean. So didn't see really too much of a relationship with that or similarity to that. Psycho, I don't know. And then Amadeus is about, Mozart and so forth. But I did think the first few ones that it returned were right on for sure. In that regard. Now, I really want to just wrap this up with the applications of word embeddings outside. It's not just used for text. Okay, so this idea of finding these co-occurrences, not necessarily just of words, but of anything actually, you can apply it. So I just went to the Nature website and just did a search on word embeddings and just seeing how it's being used. And these are relatively recent, like the last few months or so publications. And this is a deep learning system for bridging molecule structure and biomedical tech. So they can be applying it to both. Now, just deep learning, a little heads up on that. That is a type of neural network with multi-hidden layers, and that's where that deep learning comes into play. I really thought this was interesting, learning this interpretable cellular and gene, and they call them signature embeddings, right, from single cell. And this is applying it to RNN data, and that's the idea. They're trying to find these co-occurrences. So that's applied to, in the biological, right? And you can, that to me, I thought it was pretty impressive. So you can view these articles online. This one was really cool. Well, all of them are really cool, but this one's interesting because what they did, so this sounds like this is more in the neuroscience domain, representations in the human brain reflecting co-occurrence statistics of vision and language. And I thought, there we have it, right? So they use something called object-to-vec, right? Again, looking at these co-occurrences, where they identify regions of the human visual system that represent this information for which objects tend to appear together in the world. There you go, right? Appear together, right? This context aspect to it. And then embeddings, network embeddings, right? So this is low dimensional representation, right? The same idea, finding these co-occurrence. Pretty interesting, that application. All right, so let's do this. Let me open it up for questions, and then what'll be next, I'll be talking about research projects. So, and I know I've been taking some questions during, so that was fine. So if you have any other questions, let's take a moment. Okay, I guess Matt's hand, I think, went, or do we, or David?
Who's clapping?
David.
Yeah. So my question, one of my questions was about the clustering of emojis or words into different categories of context, so to speak. I assume that there is a way to, okay, so the vector for mosquito may be some vector pointing whichever direction in the coordinate space you have represented. I am assuming that there is a change of basis function such that it moves the basis vectors of the vector space onto the different clusters of context, so that like you have one vector pointing in the mosquito direction, another pointing in the bat direction, and another pointing in the rat direction. And so it would be then a sort of assignment of, you would take the original cluster and apply the basis, change of basis to get some structure in the vector representation.
Okay, oh, so yeah, I'm not sure if I would think of it as, yeah, because you're going back to the true, right? True definition of vector, right? Like,
yeah.
When you said and that's why we almost, whether we're talking about biological vectors, that's loosening the definition of vector. Word vectors.
Sorry.
Oh, no, but that's okay, because word vectors are loosening. It's also, loosening, relaxing the definition of what a vector, but that's true, right? A vector, in its true mathematical sense of the word, it is contained, right? We think of the two-dimensional, right? Magnitude and length, right? And that's what you're saying is exactly my thought when in last week's talk, when the mosquito vector, and in my mind, I'm like, how are they doing this, right? How are they getting, is it tracking magnitude and direction, direction, and how, is it capturing that? And then how is it capturing? Are there little cameras on the mosquito? That's not possible, so I was just like all over the place. And that's why I was, which speaks of my knowledge of the biological, the deep biological domain. But yeah, so we want to relax that definition. So we're not thinking of it in the true, right, vector, right, capturing, magnitude and direction, but we still can use the properties, because why? Because we are still representing them, giving it a numerical representation, right? Vectors using a numerical. That's where we're staying true to, we're relaxing it a little bit, but we're still enabling it. We're still making it, contained. It's containing numerical values. And as long as we have that, we can use the properties. We get those nice properties of vectors and makes this possible. But good question. That's because that was my mindset initially. Like, that's interesting, mosquito vector. And that was the reason for the question. Okay, so I see, go ahead.
Yeah, Bruce said that I should look up principal component analysis if I want some more information on that. And I think that is going to be my next, it's going to be my next few hours of free time. Yeah. All right. Yes. Thank you.
Yeah, no, and that's good. Principal components analysis. Yes, that is also a dimensionality reduction method as well. Okay, so I see we have a question from Taylor.
Hi, when you were first talking about word embeddings and stop words and sort of like, extracting specific words is maybe think of like when you're texting someone and there's autocorrect or autocomplete. Does text mining have any relation to that?
Yes, absolutely. When you have that auto, that's very interesting. You cued in on that. That is a type of language model. When we're doing that auto, when it's correcting your texting and it's correcting your word, how that's doing. So that brings in, right, statistics and probability. To go back to what Chris said, let's put a math all around all of it, right? Because it's about predicting. How does it know when you type or your message, hello, mom, right? And you type it mim, right? And so it's going to go back. So and see M, and maybe in the context that you're using, you meant mom, right? Or something to that effect. Or type friend, hey there, friend, FRIE, instead of N or N, you say P. It's going to know, no, looking at, because it's trained on, it's using probability to probabilistically determine what the next character could be. That's how it's able to go back and autocorrect. So yes, it's definitely related. It all falls under, it's a type of language model to make those predictions. So yes, it is using that. That was a good to realize that. And also another application, not just in texting, if you notice an email, right, when you do a reply, it also corrects. It gives you well, that's actually a little bit more. That's trained on a lot of sophisticated deep neural networks for given full expressions. But when it was doing autocorrection of words, that is, again, language modeling at its work. Thank you for the question, Taylor. That's a good observation. So far, a lot of great observations, David, Taylor. There was a few other, and of course, faculty that have chimed in. I appreciate that as well. Okay. Oh, do we have a question? I'm not seeing. Oh, let me see. If you don't mind just speaking, I'm not seeing any. Oh, I can skim through now. Okay, I can skim through. So any other questions? Let me see the chat. Oh, okay. Okay, so yeah. All right, so let's go on to research projects. Unless, if you want to just speak up, if you have a quick question. You know what, we'll have other opportunities for questions as well, but just in the interest of time, I see we're coming down to the wire here. All right, so this was a project. This was a conversational user interface. This is for stock analysis. And the idea of this, so this is just to get an overview of the system. This was utilized. So the key idea with this was creating a system that was going, instead of constructing a natural language processing or a natural language understanding engine from scratch, I was going to see what was available and just integrating it and building something on top of that. So that was this stock bot that was created. So we had, so this is kind of the overview of the design. So you would have asked a question like, what's the stock price for IBM? So there's this, this is the application server using Slack. Again, that's a public available, you can use that publicly. And then here is this tool called RASA, and that's an open source natural language processing and understanding engine. And so these were the key features of what I was going to implement, or what I did implement, was giving stock price, stock news, history, prediction, and stock sentiment. And API data, so the data for the system, stock data, financial news, and Twitter. Those were the primary data sources. And so here's just some interaction snapshots. And this is just giving you the tweet sentiment. All right, so this was going out and extracting the real-time tweets from Twitter and breaking that down. So you get this, this pretty simplistic. I like to go back and just really improve upon this, because it could be improved upon. And there could actually be an interesting study on this, because there's right now there's how should I say this, like a study as to what is the benefits compared to RASA. It is being compared to GPT-3. All right, so, and they've incorporated some features. So I'd like to go back and see how can we, how can this be extended, and then actually might have to be reconstructed as well. All right, so this is an example of an interaction. So in stock price, and then, returning that. So forecast, right? All right, so this is probably where the most work was done, all right, for this part of it. Because it's doing a prediction. This was using a recurrent neural network for handling the prediction task. And history was just going for historical data and then presenting. I will, oh, so here's the link. So I have this for you if you're interested in looking at that. That is a published paper. But I see there's ways to really revamp this possible extension. You make it, I like to make a GPT, rebuild it using GPT 2 until 3 becomes, well, I've got to look at the license for that, see if that's something that's easily accessible for purchase. All right, so this is another, this was recent. This was a publication that was just presented in December. And this is where it's specific focus on word embeddings. So the last project was really more, building a system using open source tools. This one was looking at the weight of co-occurrence frequencies. All right, so again, so we go back to knowing, we learned about word pairs. That's how we're building the word context matrix. And so this is where I collected data from Wikipedia. All right, so this is a collection. They make available this data, right? So we know Wikipedia, right? This online encyclopedia. And then the word embeddings built them, right? So built the word context matrix. And this word context matrix, right? So that little example I gave, that was a 4, right? Just for getting some intuition behind word embeddings. That was a 4x4, right? Vocabulary size 4. What for this project, we ended up with almost 200,000 vocabulary. Okay, so just giving you an idea of how important we got to reduce those dimensions to be more computationally, make them more computationally efficient. So what I did here was applied constraints. All right, so what does that mean? Apply the constraints to the frequency. I wanted to see how much of an impact would that have, if it has any impact at all. And so what you're seeing, and then reduce the dimension just using the singular, was truncated singular value decomposition. Now, here's the evaluation on the word similarity task, all right? And again, this was the most constrictive constraint, all right, of 0.1. And so what you're seeing here, so these are some words, so looking at some query words, artwork, and then the top 3 similar words. And so you can just see by looking at this that, yeah, it's returning words that are similar to these words, right? Artwork, yeah, illustrations, drawings, paintings, that certainly would fall under that, certainly is a relatedness to that term. Michigan, all right, top 3, Ohio, Illinois, Pennsylvania, yeah, for sure that there's a similarity, and so forth. So what this research, seems to, and I want to do more experiments on this, but it definitely it's promising, and it seems to suggest that it's actually the frequency doesn't have much of importance, but there's another term the variety is what I want to explore next. What is the variety on the co-occurrence matrix, and is there a way to be a little more, give some support? Is there a threshold, to be more precise, a threshold that should be met to, that we don't need to have all kinds of train it on a whole bunch of data, right? Because even the training of these models can take days. Just letting everyone know, these are not something that can be trained quickly if we're looking at a lot of data. So if there's a way we can somehow make the training more efficient, and that's what this paper, so this was published, and it's now available. It was published this was December, the talk in December, and it's now available. So if you're interested in reading that, so that's something I'm exploring as well. All right, so that's that one. And then one that I'm currently looking at, I had to tie it to COVID, right? COVID affected all of our lives. And what I'm interested in looking at is something like a longitudinal study, at least over the past 2 years, right? Of the sentiment surrounding the pandemic. I already have the collection. So I used Reddit data. Oh, I didn't say here, but it's Reddit data. And I've already collected about 600,000 posts. This is all pertaining to news, all right? And this goes back from December 2019 to just, this past month. I have both. I collected COVID and non-COVID. So I want to kind of to look at both. I haven't applied anything. I will extract the COVID probably to separate that, because that's what I'm really interested in, is the sentiment surrounding that. And then one of the as I mentioned, emoji embeddings, they made a publicly available emoji to VEC. And so I used that, and what they did, so this is the authors of that emoji VEC, they trained it on a little over 1 billion tweets, all right, for emoji prediction. So I thought, okay, that sounds like a pretty well-trained model. So I went ahead and applied it to Reddit news. And so as I mentioned, it's kind of all, I didn't, right now I just applied it to all, then I'm going to separate out the ones pertaining to the, COVID. But it is interesting, right? So we look at so I looked at the top 5. So this is from December 13th. It's a timestamp on the news from December 13th, 2019. And the top emojis, so this is kind of like, this yummy face it's delicious. And what is the topic, right? Ginger beef, Caesars, and butter tarts, right? So definitely a food related. So that was, cool that it did an accurate emoji prediction on that. And then for Beware, this is the other one. This was January 26th, 2020, entitled Beware of Coronavirus in China. And we can see right away. So this automatically, and this is automatically assigned these. This is the model, right? This emoji to VECA model. They trained on the billion tweets or so, and it gave it the mask emoji, right? And then this kind of like this anger. So that pretty accurate. And then I thought this was cool. And again, I just randomly went through, some of the results just to show, because this is still a work in progress. But I thought this one was this interesting one. So 16 accounts on TikTok. So this is the title that made cooking during quarantine bearable. All right, so that was on December 2020. And so, yeah, so we get the mask, right? Because does it recognize, it predicted the emoji here, a mask, and then you have the yummy, right? So it kind of combines a little of the pandemic, right? An emoji surrounding the pandemic, and then realize this is about food as well. So I'm so far pretty impressed what I see, and it would be interesting. So now, like, extract, right? So, and try to put together a longitudinal study and try to see, because I'm interested in seeing how has the sentiment changed, right? Since the onset of the pandemic, and then, over the past 2 years. And so that's something that is currently in process. And then something that's really, I'm just starting to look into, and this is because I just started teaching. I have a new course prep this semester on database systems. And so I'm really, and again, as I mentioned in the beginning, for the interdisciplinary, we know that database systems are, that's an interdiscipline, a discipline surrounding text mining. So I was looking at how could, for queries, I'm looking at literature to see how to generate SQL queries using natural language. And just to get an idea what that's all about. So query, this would be a database query. This is why we have a class on database systems, because we have to learn how to query a database. So you have these clauses, right? The fundamental ones are select and from. And so what you have here is a little more of it's using a join. So it's comparing 2 tables. All right. So this is the question, the natural language question. And it's like, how do we take that natural language question? So you see there's some entity recognition, right, going on here. Concept, there's definitely this extraction of pets, French, students, older. So we're using those in trying to automatically generate this query. This would be the actual query. Can it be automatically generated? So there's some interesting research going on in this space that I like to definitely, explore deeper, since I'm hoping my database class becomes a staple, because I really see that can go a lot of places. All right, so let's wrap up the research part with a Q&A. I know we're on time. If anyone has to leave, this was being recorded, so you can watch this. If you do have to leave, we'll just kind of go on and kind of wrap this up. But any questions on the research or the talk, we can do it all here, and then we'll just wrap it up with teaching. Let's see, anything in chat? Okay, so I don't see any. Okay, so no question. Okay, so let's just wrap it up with teaching here. Okay, so as mentioned in the introduction, the nice introduction from Matt, so text mining and analytics is the course, right? So it's going to be the 5th year offering this fall. And just what does the course entail? We do cover math review. We go over probability and statistics and some key, ideas, topics from linear algebra, really to support what was discussed in this talk. It has a Python orientation, right? We focus on, we create these Jupyter notebooks, and we learn various libraries that surround machine learning. That's scikit-learn, that's a machine learning library. NLTK for natural language toolkit. Spacey, this is also a natural language processing surrounding, especially with entity extraction, recognition as well. And then with the visualization that we saw, right, for viewing embeddings, very useful. And then we also get really heavily into social media data, and we'll be working with, we have worked with, and we'll continue to work with Twitter, Reddit, Wikipedia, and I'll see about some others as well. I like to freshen up the course at every offering, every time I teach it. And then there are some key, because it's data mining, right? Because we learned the interdisciplinary at the start of the talk, that we know classification and clustering are key data mining. So we do focus on making sure we get an understanding of that and how that's used in the context of text mining. And then I also want to mention, since 2020, this has been a CRE course, which means course-based research. We tie it to a course-based research, have a project that's research-oriented. In 2020 was on fake news detection, and then sentiment analysis in 2021. All right, lastly, senior project methodology, because I know the whole point of this talk for the seminar, it's to get you right thinking about, this is, early on, start thinking about senior projects and how we want to approach it. And this is my methodology of how I approach senior projects. And this is where it incorporates my industry experience on project and software management. We start off with a proposal, all right? And it's important that it's a culmination of your concentration, all right? If you're in software engineering, I'm going to be looking for, that you surround it pertaining ideas surrounding software engineering, right? Scientific computing and so forth, all right? Want to make this a culmination of what you've done through your whole degree program. The orientation can be research, exclusively research, or software system, right? Developing the system, or both, little combination of both. And then the approach I take is this weekly status, right? So we have a project plan, right? We kind of think ahead of we chart out our semester, and then we come up with a risk and mitigation plan. So you think into this at the start, what are things that could impact the schedule? And yes, since the pandemic hit, that is something I ask students to put in their risk. I could be out for 2 weeks. So how do you plan to mitigate it? It's not just identifying a risk, but it's also, what is the plan to mitigate that risk? And then issues that come up, because let's be real, in computing, when you're developing, there's always going to be issues. Okay, tells me, if you're actively involved, if you're coming up with issues, weekly issues, coding issues, right? You couldn't get this API to work, right? It's not working, and it can't get the wrapper surrounding it, or whatever it may be, right? We got to identify them, and then more importantly, how do we resolve them? And that's also important, right? So we expect the weekly status presentation, and I'm really cluing in on, issues encountered and how they were resolved. And then also, and this is really the importance of the weekly collaborative, we all meet as a team, even if we're working on separate projects, because we all can help each other as well. There's an important collaborative aspect to that. Another thing that I really stress is for the paper, because we're writing a paper that's a deliverable, we learn LaTeX, all right? And that is, every computer scientist and mathematician, right? This comes from mathematics. It actually was created by a very pivotal person in the field. He wrote a lot of great computer science books. His name is Donald Knuth. And so he created this years ago, and it's still very useful. So we're going to learn that. And it's a lot of code. It's very code-based. So computer scientists especially love it. And then just your deliverables. And then, just mention, if you want to make this a text-based project, this is good early on, all right? Early on, now that you're getting introduced to this with the seminar, this is a great seminar that really was spearheaded by, this series was spearheaded by Dr. Johnston, and really good idea to be introduced this early on, so you can start planning ahead, right? So yeah, I think I want to do something in text mining, so let's arrange, right? We have a text mining course, maybe get a directed study, which I'll talk about. This is the last thing to start moving you in that direction. And directed study, right? We can have it on text mining or anything of the interdisciplinary topics that were mentioned, okay? And this could be 1 to 3 credits. And it really will be similar to a senior project. That really depends on the credits that are taken. So if you have like a 1 credit, we'll see this as more exploratory, a deliverable presentation, typically on the knowledge acquired. Probably should add, I would like to also see a paper Yeah, definitely something, substantial there. And then 2 to 3 credits, we're getting deeper into it, right? Maybe addressing a problem, a deliverable will be a paper, and then a code base as well. So yeah, so that sums up my teaching, in terms of the course, senior project, and direct to study and possible options there. Well, thank you everybody for your attention, and let's take Q&A for teaching, research, seminar talk, anything you can ask. I know I went over 14 minutes. Any questions? All right, so okay, so no question. Oh, I didn't check the chat. Let me see. Canadian food. Okay. Oh, do you have Canadian food for us?
Yeah.
I would love it. I am hungry.
You had the one slide with butter tarts and Caesars, which I believe are both quintessential Canadian.
Oh, really?
Or drinks, I guess, if that's the Caesar you mean.
I did. Oh, interesting. Okay, so that's cool. That's really cool. Okay, so yeah, so we did went a little over. Okay, so if you don't have any questions now, that's okay. You can email me as well. All right, and so I'll be involved in the seminar. I'll be doing the introductions. Give Matt a break. He's done so much so far for the next several speakers. So yeah, and you can send me email question. Oh, here, let me put my email in the chat. So you can email me. Oh, no, I'm not sending it to everyone. Okay, there you go. And I'm pretty accessible. All right, well, I think we'll wrap this up. And yeah, thank you again. Thank you, everyone. I look forward to, this is a great seminar. I guess us introduced to everything. And yeah, we can start planning ahead. That's important, right? It's computer science, try to plan ahead and actually go ditto for mathematicians as well. Planning is important. All right, well, thank you so much, everyone.
All right, thanks everyone. Thanks, Paula, for the great talk. And we'll see everyone in 2 weeks when Tao Lu will introduce us to some of the research that he's working on. All right,
okay.
So bye for
All right,
now.
bye, everybody.